I'm going to be doing the Year 12 assessment paper here, 2019. I've got to apologise in advance, I don't have all my stuff here, so my lighting is pretty poor, so hopefully you'll be able to see this. The roller coaster is raised to a height of 65 metres, released from rest. What's the maximum possible speed of the car? You can do this two ways. You can either use suvat or energy. I think energy is easiest. mg delta h equates to, so the gravitational potential energy lost equates to the kinetic energy gained, as long as that's in the maximum case. The m's cancel, so it doesn't matter what the mass of the roller coaster car is. And we have v squared is equal to 2g delta h. So let's solve that. So 2 times by 9.81 times by delta h, 65. And we need to square root that answer, giving us 35.7, so 36. So the answer is C. Two bodies of different masses undergo an elastic collision, keyword there, elastic, in the absence of any external forces, which row gives total effect on the kinetic energy and the forces. Well, if it's an elastic collision, then the total kinetic energy before is equal to the total kinetic energy after, so it has to be A or B. And then the magnitude of the forces, down to Newton's third law, the forces must be the same on both masses. So the equal and opposite forces. Their effects might be very different. If you had a smaller mass, then the force on that smaller mass would cause a greater acceleration, so that smaller mass would end up going faster. But that's not what the question asks. So the answer to that one is A. We have a decay occurring here. The quark structure of particles is shown in the diagram. Deduce the name of particle X. Well, up, down, down. So if you look at the formula sheet, you can see the up quark has a charge of plus 2/3 and the down quark has a charge of negative minus 1/3. So that charge adds up to 0. So it's going to have to be the neutron. State the type of interaction that occurs in this decay. Well, we have leptons over here, and so it can't possibly be the strong force. It has to be the weak force, because strong is only between hadrons or quarks, and if it contains anything else, it's got to be the weak force. State the class of particles to which W minus belongs. Notice there's quite a lot of state questions in ones on particles, because they ask a lot of knowledge-based questions, so you just need to learn your stuff. So W is a gauge boson. Show clearly how charge and barrier number are conserved in this interaction. You should include reference to all the particles, including the quarks, in your answer. Lots of you did not include reference to the quarks. So we're going to do charge first. So we start with up, down, down. So we start with plus 2/3, that's the up, down, down, minus 1/3, minus 1/3, and that's all e's. So that's this one, goes to plus 2/3e, minus 1/3e, that's the up and a down, and then this up here, plus 2/3e, plus the electron neutrino, antineutrino, has no charge at all, so 0. and then minus 1e for the electron there. And you add all this up and you get 0 is equal to 1 minus 1. So that actually works. And then we also need to do baryon number as well. So baryon number, and each of these has a baryon number of plus a third. So it's a third plus a third plus a third goes to here, a third plus a third plus a third plus 0 plus 0 for the remaining things. So baryon number is also conserved. Name the only stable baryon. That is a proton. You need to know that. Oops. A muon is an unstable particle. State the names of the particles that are produced when a muon decays. Well, let's just write the decay of a muon over here. So we have a muon goes to an electron. Now we have to balance electron-lepton number, so we also need an anti-electron neutrino, and we also have to balance lepton-muon number. So here you've got the lepton number of the muon is a +1, so the lepton-muon, to balance lepton-muon number, we need a muon neutrino. So that's a mu. And we need the particle, not the antiparticle, because we started off with a particle. So that's got to balance the lepton number, and that balances the lepton number of the electron that we've made from the decay. So these are the three particles. So we have an electron, we have an electron antineutrino, and we have a muon neutrino. Okay, easiest if you write out a decay equation and balance it first. Question 4. There are two ways you can do this. Energy is the easiest, but you could also do it SUVET. So we just do mg delta H is equal to a half mv squared, like so. The m's cancel, and we want to find out what the velocity would have been at the bottom if there were no friction. So we get v is equal to 2g delta H all square rooted. So let's work out what that is. So we've got 2 times by 9.81 times by delta H. The height difference is 3 meters. Then we need to square root that answer. And we get 7.6, so 7.67 meters per second. Actually, I've just realized you don't even need to do it. Actually, I've just realised that we've gone another step, because we're actually just going to turn this straight back into a kinetic energy. So we needn't have bothered doing this, but never mind. So we're going to square this and times by 0.5 to find the kinetic energy if there was no friction. So the kinetic energy is equal to, I didn't times by the mass. The mass is there. So the kinetic energy is 73.575 joules if no friction. So what is the real kinetic energy? So the actual kinetic energy is going to equal 0.5 times by 2.5 times by 5 squared. So the actual kinetic energy is 31.25. We take that away from this, and I just want to do let's make it positive. So that is the amount of energy that we've lost, the difference between the kinetic energy it would have had if there was no friction and the kinetic energy that it actually does have. And then we can just use force is equal to work done times by distance. So the force is equal, that's not true at all. You can tell I'm quite tired. The work done is equal to the force times by the distance. So the work done divided by the distance, which is this length here, which is 5 meters, gives us the force, and the force is 8.46, so it's A. Okay, there were different ways you could do that question. I think that's the easiest way of doing it with energy. When a nucleus of the radioisotope this decays by beta, so if it decays by beta, its mass number will stay the same, but this number will go up by 1, so it's going to be this one or this one. How many protons and neutrons are there? Right, so just be careful. Some of you put this one because you thought it was protons and mass number. That's protons and neutrons. These two have to add up to 65, so it's this one here. Okay, let's see. When light of a certain frequency greater than the threshold frequency of a metal is directed at the metal, photoelectrons are emitted from the surface. The power of the light incident on the metal surface is doubled, which row shows the effect on the maximum kinetic energy and the number of photons emitted per second. Right, so if the power is doubled, we haven't changed the frequency of light. So if we haven't changed the frequency of light, then that means that the maximum kinetic energy is going to remain the same. Remember that you had the energy of your photon is equal to phi plus Ke max. So even if we increase the power of the light, we don't change the energy of each individual photon, we just have more photons. So this hasn't changed, so that won't change. So the maximum kinetic energy has to remain unchanged. But we have increased the power, so more photons are hitting, so that means that we're going to have more interactions. So we're going to have double there, so that's going to be C, like so. Define the term work function. Well, to define the term work function, it's just a book learning thing. It is the minimum energy required to eject a photoelectron from the surface of a metal. That's what work function is. Show that the work function of the metal is approximately 4 times 10 to the minus 19 joules. Use data from your graph in the calculation. So we're going to use this equation here, that the energy of a photon is equal to the work function plus the kinetic energy max. So we need to use something from the graph. So remember, whenever you use data from the graph, then you should always mark it on the graph where you got it from. So where should we pick? Well, we could make our lives nice and easy and pick this point here, couldn't we? So that's 550 nanometers and 0 kinetic energy. So that is the threshold frequency there, of the threshold wavelength, which will give us the threshold frequency when the kinetic energy is 0, when we're only just getting photoelectrons off. So from graph, lambda equals 550 times 10 to the minus 9 meters, and Ke equals 0. Okay, so now we need to solve this. You don't get much space. I'm going to write it a bit bigger down here. So E is equal to HF, which is equal to HC over lambda, which is equal to 6.63 times 10 to the minus 34 times by C, which is 3.00 times 10 to the 8, divided by lambda, which is 550 times 10 to the minus 9. Okay, so 6.63 times 10 to the minus 34 times by 3 times 10 to the 8 divided by 550 times 10 to the minus 9 gives us this. E is equal to 3.616 times 10 to the minus 19. Now, using this equation here, that's what phi is equal to, because E is equal to phi plus KE max. So therefore, 3.616 times 10 to the minus 19 is equal to phi plus 0. So that's the answer in joules. Okay, shouldn't write it like that. Naughty of me. Phi is equal to 3.616 times 10 to the minus 19 joules, which is approximately equal to 4 times 10 to the minus 19 to 1 significant figure. You were allowed a range of answers there, and the range of answers depended on which location on the graph that you took there. Monochromatic radiation is incident on the metal surface. Photoelectrons are ejected with a maximum speed of this. Determine the wavelength of the incident radiation. Okay, for this one, a lot of you used this value without thinking you needed to work out what the kinetic energy was. So we're going to use the same equation again. So HC over lambda, that's going to be our E, is equal to phi plus KE max. So lambda is going to equal, move that up there, everything else down there, H times by C divided by this. So we've got phi, which was 3.616 times 10 to the minus 19, plus, and the kinetic energy max is a half times by the mass of an electron, which is on your data sheet, and it is there, 9.11 times 10 to the minus 31. Times by this squared, 4.6 times 10 to the 5 squared. Okay. Oh, and these have values as well, don't they? So this is 6.63 times 10 to the minus 34 times by 3.0 times 10 to the 8. Okay. Here we go. And this will equal our answer. So, okay, we'll do this equation here. I'm going to start down here. So we've got 0.5 times by 9.11 times 10 to the minus 34 times by brackets 4.6 times 10 to the 5 close brackets squared. Okay, so that's the maximum kinetic energy there. Seems a little low. Oh, I put in 34 there. I meant to put in 31, didn't I? That seems better. Okay, and then we're going to add that to our work function, which is 3.616 times 10 to the minus 19. So that's that bottom row there. And then we're going to have 6.63 times 10 to the minus 34 times by 3 times 10 to the 8 divided by what we just worked out. That's much better. So lambda is equal to 434 nanometers. Okay, so that's that bit, and that's that bit there. So there's quite a bit to do there, but it's actually just using the same equation each time. It's not too difficult, really. I think, as I said, most people put this in instead of the kinetic energy, and they didn't remember to square it in times by half the mass of an electron. Okay, this question didn't go very well in general. But again, it's just an energy question. It's just using mechanics and a bit of geometry. So show the maximum possible speed of the water as it arrives on the turbine is about 40 meters per second. Well, we've got a drop of 90 meters. So again, we just use energy conversion, loss of kinetic energy, loss of gravitational potential energy equals gain of kinetic energy. So mg delta h is equal to a half mv squared, the maximum possible. Of course, the masses cancel, and we've got v is equal to the square root of 2g delta h, which comes up very often. So 2 equals to the square root of 2 times by 9.81 times by delta h is 90 in this case. So we've got 2 times by 9.81 times by 90, and we want to square root that, and we get 42 meters per second. Okay. The volume of water flowing into the turbine every second is this much. Estimate the radius of the intake. So if you think of the tube there, the pipe, then this much water, if this water travels all the way to here in 1 second, then this has a length of 42 meters because it's traveling at 42 meters per second. The cross-sectional area of the tube is there, and that times by that is equal to the volume, which is what you've got given there. So 42A is equal to 3.5. That means and A is pi r squared, so pi r squared is equal to 3.5 over 42. So we can do this. That's 3.5 divided by 42 divided by pi and square root it. And we get r is equal to 0.16029. So 0.16 meters to 2 SF. The water leaves the power plant at a speed of 12 meters per second, and it arrived, remember, at 42. We need both of those numbers in a moment. Calculate the maximum possible power outputted by the turbine and the generator. Give an appropriate unit for your answer. Okay, so we need the kinetic energy pre-turbine. That's equal to a half times by the mass times by the velocity squared. So it's a half. Now the mass is going to equal the volume, so 3.5 times by the density, 1000. So that is the mass. Okay, and then times by the velocity squared. Well, the velocity before it hit the turbine was 42 meters per second squared. And the kinetic energy after is equal to a half times by 3.5 times by 100. No, sorry, 1000 for that. So it's the same mass. And this time times by 12 squared. So, when we want to find the difference between these two. So delta KE is going to equal this one, take away this one. So let's work out what these are first. I think it's probably the easiest way. 0.5 times by 3.5 times by 1000 times by 42 squared is equal to 3087,000 joules. And this one divided by 42 squared times by 12 squared is equal to 252,000 joules. So I want this one to take away this one. So would have been good time to use the memory on your calculator there. But 2,835,000 is the joules that is lost, but this is the amount of water flowing each second. So power is equal to delta KE over time, which is equal to 2,835,000 over how much time? Well, it's 1 second. So it's going to be 2.84 megawatts is the most appropriate unit to put there. Right, these answers here lacked the detail required at A-level. Give two possible reasons for the energy loss. I want to know what the energy is being transformed into, what force or process is doing the transformation, and also where that's occurring. So could be lost as heat in the turbine due to maybe the friction in the bearings, for instance. So I've said where, I've said what the force is, and I've said where the energy ends up. Okay, we could have lost as heat in the generator due to the resistance of the wires. So electrical losses. You could also have maybe due to lost as heat due to friction between the water and the edge of the tube and the turbine blade itself. So those are two possible losses of energy. These two are the main ones, the friction of the turbine turning and the heat losses, the electrical heat losses. A stone is projected horizontally by a catapult consisting of two rubber cords. Cords obey Hooke's law are stretched and released. When the cord is extended by x, the stone is projected with a speed of v, assuming that all the strain energy in the rubber is transferred to the stone. What's the speed when the cord is stretched by 2x? Right. So this is an energy equivalence one. Instead of gravitational potential energy to kinetic energy, it's energy stored elastically to kinetic energy. So we have a half kx squared is going to equal a half mv squared. Okay, so if I change the stretching of the string to double, then that will quadruple. In order to match this, v needs to double because then that will quadruple. So it's got to be that one. Two unpowered toy cars are released from rest and travel down the track. P has twice the mass of car Q. There's negligible friction. Well, the velocity that they've got here is going to be based on this. mg delta h is equal to a half mv squared. The m's cancel, so it's independent of the fact that they've got different masses. Right, what's the quantity is the same for Q and the gravitational potential energy at x. No, the heavier one will have a greater gravitational potential energy. the accelerating force at x? No, the more massive one will have the greater accelerating force as well because it's got a greater weight. The velocity when they arrive at y, yes, they will be the same. The momentum when they arrive at y, no, they've got the same velocity, but they've got different masses, so therefore they'll have different momenta. Okay, hopefully that was helpful. I'll try and get this uploaded as soon as I can. Right.